Hello, and thanks for tuning in to this Maya MEL script demonstration. This is not a tutorial, but a demonstration of a small utility I wrote in MEL script and decided to show it here to get some possible opinions and feedback on its usefulness, and maybe some input on how to improve it. What this script does is calculate the 2D image pixel position of a 3D world space object. So if I am viewing a scene through a specific camera and I want to know the 2D pixel position of this cone in the camera's image frame, I can easily determine that and even write out sequential tracking data for the animated objects using this tool. I have it on my tool shelf, so I'll just click on this icon that says 3D to 2D and I get this small, simple interface. The orange banner at the top is not a control widget, but serves as a basic instruction or reminder to the user on how to use the tool. One of the first steps is to select the object or objects that you wish to determine the pixel position for. The type of objects this will work on are anything with transformation data, which includes transform nodes, geometry vertices, CVs, curve edit points, IK bones, locators, particle emitters, and even individual particles. You can select any combination of objects and get a frame-by-frame output of the pixel position of each object. So for now, I'll just select the cone. The next step is to select a camera view through which the object's 2D position will be determined. Simply follow the instruction in the Camera text field and left mouse click on the field to get a pop-up menu of the available cameras in the scene. This will include all perspective and orthographic cameras that currently exist in the scene. So if a camera is created or deleted after making a selection from this menu, you simply have to re-click on the menu and the menu items will refresh with the currently available cameras, so you don't have to reopen the entire window. I'll select the camera I am currently viewing through the viewport. The camera text field then turns green to indicate that I have a valid camera selection. The next thing I need to do is provide a render resolution of the image space that the calculation will be performed for. By default, the image height and width values are taken from the Device Render Settings window. The last step is to press the Calculate Pixel Location button, and I get a pixel location readout accurate to 1/10 of a pixel. The actual values include more decimal places, but this output is truncated for simplicity and ease of evaluation. Just for verification, I'll move the cone to the upper left of the render gate and calculate, and see that the pixel position of the cone is near 0, 0. If I move the cone to the far bottom right and calculate, I get something close to the total image resolution of 1920 by 1080. The orientation of the image origin can be changed, which I will cover a bit later. Just as a side note on the choices of possible camera viewpoints, Maya allows you to view a scene from the perspective of any object in the scene, such as a light. To demonstrate, I have a spotlight in this scene, so if I select the spotlight in the outliner, then go to the Viewport Panels menu and choose Look Through Selected, I get a perspective camera view from the position and direction of the spotlight. I'll open the spotlight hierarchy in the outliner and I can see the new camera persp shape underneath. To focus the spotlight and camera view on an object, I just select an object, such as the sphere in this scene, then click on the View menu in the Viewport menu bar and choose Look At selection. Now the spotlight and its view camera are directed at the sphere. To choose this new camera viewpoint in my MEL tool, I just left-click on the camera text field and get a new menu containing the spotlight camera. It is important to note that the camera menu displays the names of the transform node parents of the cameras, not the actual camera shapes. I'm not sure of the usefulness of getting tracking data of an object from the viewpoint of a light, but the option is there. I'm going to change the camera back to the regular camera viewpoint. Now, it is important to note that the render resolution values in the tool interface do not need to match the default render values. The tool will make its calculation based on any image dimensions that the user chooses within the tool, regardless of the device render settings. These initial values that are set on startup are simply a convenience, based on the assumption that the default render settings are the final target dimensions of the intended output image. The render resolution settings of these windows are not connected, so if I change the default render settings to something like 2048, it has no effect on the tool settings. The MEL 3D to 2D tool essentially operates on its own input. This is intended to provide the user more flexibility for experimentation without having to continually change the values in the render settings window. Observe, though, that if the render resolution values in the 3D to 2D tool are changed to a value that differs from the Maya render settings, the number fields in the tool will turn red to indicate that they do not match the Maya render settings. This is, again, a convenience device to remind the user that the current tool resolution values do not reflect the current render settings, but does not affect the calculation. It means that any calculation made using mismatching resolution settings will result in an incorrect pixel position of the evaluated object relative to the final output image. So ultimately, these values need to match to get a proper result. Note also that this calculation assumes square pixels, and currently does not accommodate anything other than a pixel aspect ratio of 1. Now I'll close the render settings window since I don't need that anymore, and we can move on to the output options. I will open this part of the GUI by clicking on the collapsible title bar. The various options are Image Origin, which defines the XY00 pixel coordinate of the output image as the top left corner of the image, the bottom left corner, or at the image center. Image units are the units or numerical convention in which the position in the image is expressed, either in pixels or normalized one-based units. Output range is the frame range for which the data is being read. The current frame option provides a result for only the frame at which the timeline is currently set when the calculation button is pressed. Range slider provides output for all object positions within the frame range set by the timeline range slider. All frames provides output for all object positions within the frame range set by the complete timeline range. Write data to specifies where the calculated data is displayed for the user, either in the script editor or written out and saved as a text file to be imported by other software, such as a compositing program. I'll briefly demonstrate each of these options for clarification. To demonstrate the differences of image origin, I'll use this cone to mark the desired position in the frame. I'll set all the options to their default settings and move the cone to the top left of the render frame. The render aperture is the darker outside frame. The inner frame is the camera aperture, but the render aperture is what we are interested in since that is what defines the complete frame of the output image. I have deliberately made the camera aperture different than the render aperture to illustrate a specific feature of this tool later on. So with the cone positioned at the top left of the render frame, and our camera view chosen, and the image option set to top left, I will calculate the pixel position of the cone in the render frame. I get something close to 00, but not exactly, since I have not positioned the cone precisely in the corner of the frame. Now, if I change the option to bottom left and recalculate, the X width value stays the same, but the Y height value changes to almost the total height of the image resolution, since the height is determined from the bottom up. Next, if I change the option to center and recalculate, I get a negative X value that is nearly half the width of the frame, and a Y value that is nearly half the height of the frame. If I move the cone to the center of the frame and recalculate, I get pixel values close to 0, 0. Now I will change the image units from pixel to normalized. I'll move the cone to the bottom right corner of the frame and change the image origin back to top left and recalculate. Now I get an X value that is close to 1.77, which is the aspect ratio of the image frame, and a Y value close to 1. This means I am using normalized values based on the aspect ratio of the image with the image height defined as 1. If I change the image origin to center, I get values that are 1/2 the normalized height and width. The Y value is negative since the cone is positioned below the image center. For the other two options, I'm going to change the units back to pixels and the origin to bottom left, and reposition the cone. If I change the output range option to range slider, I will be calculating a number of animated position values. I have several animated objects in this scene that I want to output image positions for. I'll scrub through the timeline to quickly show you what the scene is. There is a rolling ball on which I want to track a single vertex, a stationary cone, an animated light, and a particle emitter from which I want to track a single particle. First, I need to see the particles, so I'll temporarily move the range slider to -5 to set the emitter. Then move the time frame back to 1 to see some particles. I'll right-click on the emitter to display the component menu and choose Particle. Now I can select an individual particle to track. Next, I'll shift-select the spotlight and the cone. Last, I'll right-click on the sphere to display its component mode and choose Vertex. Then select a vertex on its surface. This will provide me with 4 various objects to demonstrate the next output options. The camera is also animated to provide some extra motion and perspective to the scene. Now I'll display the script editor, clear the history, and with the output option set to Script Console, I'll click the Calculate button. Maya quickly runs through the animation range once for each object, and I get the output in the script editor. First, I have printed out a common header for the data that describes the conditions of the scene: the image resolution, the image origin, the image units, and the view camera. Then, for each tracked object, I have printed a header identifying the object and the labels for each column of data: the frame number, the X dimension, and the Y dimension. The header information is commented out for easy parsing of the data when read by another application. This is a simple and common format for many applications. To show that, I will output the same data again to text files using the text file option. But before I do that, I need to reset the animation for the particle emitter. I'll click the Calculate button again, and now a file browser appears. I'll navigate to my desktop, where I have made some temporary folders to contain the data. The title bar of the browser window displays the object of the data being written, so I know what to name this file. I'll just call it Particle. The file extension type is automatically set to .txt. I'll then click Save. Maya runs through the animation for that object, and presents another browser for the next object. So I just repeat the process, exporting an individual file for each object. The script editor prints confirmation of successfully writing each file to its respective location and closing the internal file ID. To test the reliability of the output, I'll import the tracks into Nuke, but first I need to render a sequence of images through the camera. Again, I need to reset the animation for the particle emitter. I'll open the render view and from the view menu change the render camera to my output camera. I have already set my render settings to hardware render a wireframe of the scene for easier interpretation. Then I'll just click the Render Sequence button to render the images out to disk. Next, I'll go into Nuke, which I already have open. I'll press the R key to read in the images I just rendered. In the File Properties, navigate to the desktop file and accept. Press the 1 key to connect to the viewer, and I can now see my images. Now I just need to import the track files I saved out. To do this, I need to create a track node in Nuke, so I'll right-click on the image node and select Transform Tracker. In the Tracker Properties, I'll add track to create a new track. Then, to import my track file, I right-click on the created tracker and select File, Import, Time plus Value, ASCII. That will present me with a file window with which I can navigate to my track files and select one. As I scroll through the frames, you can see the tracker is precisely following the object, and you can see a close-up of the tracker in the tracking thumbnail to the left. I'll continue to import the remaining tracks. One useful item to note is that this tool provides tracking data for objects outside of the rendered frame, as you will see with the track of the spotlight as it exits the frame. This offers an advantage over post-render tracking, in which the location of any object outside the frame would be lost. This method also permits you to track objects not ordinarily seen in a render. Now that you have seen how this tool basically works, there are a few finer points I'd like to clarify. One regarding the discrepancy between the camera aperture and the render aperture. I mentioned earlier that the render resolution gate is what is important since that defines the boundaries of the rendered image. Normally, the camera aperture and render aperture will be the same aspect ratio, but that is not really necessary for this tool. The relationship between the resolution aperture and the camera aperture will determine the image position of any object in the scene. This relationship is determined by the Fit Resolution Gate attribute of the Camera Shape node. I'll select the camera in the outliner and open the attribute editor. Under the Camera Shape attributes, open the Film Back options to find the Fit Resolution Gate attribute. This has 4 optional settings: fill, horizontal, vertical, and overscan, and they affect the field of view captured by the resolution gate, depending on the differences between the 2 aspect ratios. I will quickly demonstrate this difference and how it affects the position of objects in the rendered frame. With the Fit Resolution Gate set to overscan, I will position the cone at the top left corner of the render gate and set the tool options back to the default: origin top left, pixels, current frame, and output to script console. Now I'll capture the cone position in the frame, which should be close to 0, 0. Next, I'll reselect the camera and set the Fit Resolution Gate to Fill. The relationship between the resolution gate and the camera gate changes, so that now the resolution gate is completely contained within the film gate. This narrows the horizontal and vertical field of view captured by the resolution gate, so that now the cone is far outside the borders of the image frame. If I reselect the cone, which has not been moved, and recalculate its position, I get very different results. Now the X and Y positions of the cone are far into the negative values outside the frame. The pixel location is correct for this render aperture-camera aperture relationship, but it shows how different settings can change the apparent position of a rendered object, even though neither object position nor the camera aperture or render image dimensions have been changed. No matter how the Fit Resolution Gate attribute is set, this tool will calculate the correct pixel location of an object inside or outside of the render frame. One other camera attribute that this tool will accommodate is the lens offset or principal point. The lens principal point is the position of the lens optical center relative to the camera aperture. Ideally, the lens optical center would fall precisely upon the center of the camera aperture, which is normally how a CG camera is defined, but rarely so for a real-world camera. A common example would be when a full aperture film gate is used within a 35mm camera body that has an Academy-centered lens mount. The Academy lens center is shifted relative to the film frame to make room for the soundtrack area on the side of the frame. When a full aperture film gate is used in such a camera, the soundtrack area is exposed, which adds extra area to the side of the frame and in turn displaces the apparent position of the lens center. Ordinarily, this does not seem like a big deal, but it wreaks havoc when trying to match perspectives between CG and real-world cameras. One way of dealing with this discrepancy is to offset the CG camera film gate to align the gate center with the background image lens center. This is done by manipulating the camera shape horizontal and vertical film offset attributes. To display the lens principal point in the camera view, open the Display options in the Attribute Editor and check on Display Film Origin. This displays a small circle within the gate, which moves along with the captured scene when the film offset attribute is changed. This 3D to 2D tool automatically accounts for any changes to the film offset attribute, even if it is animated. The last thing to mention is that this tool includes brief user instructions which are accessed through the collapsible form at the bottom of the window labeled Instructions. Click on the arrow to open the instructions and you will find them segregated in tabs according to topic. These are an encapsulation of the same instructions covered in this video. I hope this brief presentation made sense, and if you happen to find this tool useful, please say so in the comments, or offer any criticisms or suggestions that might improve upon its usefulness. Thanks for watching.